Chapter 10, Section 8, last section of Chapter 10, we're going to talk about a new number system. With this radicals, especially when we have even nth roots, we have a real issue if there is a negative that occurs underneath that, like the square root of a -4. There is no real number solution to that. So what they've done is they're going to put together a new number system to deal with these issues like that. And when you end up with a complex number system, it allows us to solve equations like this one here, where they talk about x squared plus 1 equals 0. And so if you solve this, you'd end up with x squared equals a -1, and you'd try to get the square root of both sides, and you'd end up with the square root of a -1. So what they're going to introduce is this number I. Basically, it's a letter, but it's going to represent a complex number. And they put some rules, and this number doesn't have per se a value. It has, in a sense, that when you manipulate it or you square this I, you get a -1. And that's this number I. It says I is a unique number. So it's unique, and just like a prime factor of a real number is a unique thing. I is a unique number. You can't have this correspond to more than one thing. That's another way to say that. And it says for which I is equal to the square root of a -1. So they basically deal directly with this issue. Or another way to say this, if I squared both sides, I squared is equal to -1, which is probably the more useful way to think about this. So we're going to use this to deal with the even nth roots of negative numbers. So I can do some things, and before I talk about it too much, I'll just show you what they do in the book, which is a really elegant solution to this issue. So express in terms of I, this imaginary number, the square root of -7 is the first one. Well, they take the square root of -7 and they say, well, that's really -1 times 7. So we could say that that is the same as a square root of a -1 times the square root of 7, which ends up to be, by this rule, the square root of -1 is I. Another way you can do this, and we'll use this later on too, I could say this -1 is really equal to I squared, isn't it? So this is really I squared times 7. So we can take the square root of I squared and get -1. Another way to talk about that. And they show it two different ways. I square roots of 7, or the square root of 7 times I think make sure that this is not under the radical. So just like when we have numbers times square roots of anything, it's probably a better method. You're going to have a lot less errors if you put it out in front of the radical. Well, -16 here is square root of -1 times square root of 16. So you end up with 4I, or I times 4, okay? And so on. Well, what they're going to do with this new number, in a sense, is create another number set. And what we're going to talk about here is that these imaginary numbers, and they're going to define this in a way that we can deal with what do we do with this thing that we can't seem to have any operations occur with, and it does look like a variable, but it has a real specific definition of what that is. It says an imaginary number is any number that can be written in the form of a plus b times I, or bi, where a and b are real numbers and b cannot be equal to 0. In other words, there has to be some value times I. Okay, these are what we call imaginary numbers. We let them do, it says don't let the name imaginary fool you. Imagining numbers appear in fields such as engineering and physics, or physical sciences. They're, the following examples are imaginary numbers. 5 plus 4i. So here a is 5 and b is 4. See how it fits that definition of an imaginary number. Square root of 3, which is a real number, minus pi, which is a real number too. That's the relationship between the circumference of a circle divided by the diameter of the circle. And which we don't know the exact values for either one of those. We can't make them rational, and we'll talk about number sets here again. They show a nice diagram to illustrate where we're at with this relationship between number sets. So what they're pointing out here is that a is a real number and b is a real number. And square root of 7 times I, well, in this case a would be 0. It'd be the same as 0 plus the square root of 7 times I. Well, 0 is a real number, and b is square root of 7, that's a real number. So these are imaginary numbers. Where if I just had 2, that is not an imaginary number. That would be, a would be 2 plus 0 times I, where it tells, hey, b part, the number times your I, should not be equal to 0. Now the union, or basically the combination of all the imaginary numbers and all the real numbers, they're going to make a new number set that they're going to call the complex number system. The complex numbers are basically any number that can be written in the form of a plus bi, where a and b are real numbers. Now in this case, in the complex number system, a and b can be 0, because if b is 0 in this case, we have a real number. So in other words, the complex numbers include all the real numbers. So it's kind of building on here. They're saying, oh, let's add this to it. It's not saying this is a separate thing. This is just a bigger number system, and the real numbers are a subset of the complex numbers, and the imaginaries are the addition. So you have the imaginary numbers and the real numbers combined, they make the complex number set. So here's examples of complex numbers. 7 plus 3i, 8. In this case, b is equal to 0, but that's still in this number set. It's just a real number, and so on. And if they're both 0, that's fine too. And then when they talk about pure imaginary numbers, though, they're talking about that b cannot be equal to 0. So there's a lot of language here, but let's start looking at some diagrams that can illustrate that. And here's a good one. I kind of like Venn diagramming a lot of times, which is circles and circles and so on, and they show the relationships and intersections and stuff like that. But here in this top box here is a complex number system, and they got examples of those. There's an infinity of those, right? So they're just giving examples of what can be in here. Well, what makes up this complex number set is this thing called imaginary, or pure imaginary numbers, where the b times I is not equal. In other words, you're going to have some value of I represented in this pure imaginary number set. And here they got the square root of -7, which would be I times the square root of 7, right? And then the real numbers, which are all the rational numbers and irrational numbers. And it's very similar right here. We got imaginaries and reals make this. Let's look at real numbers again. That's what made real numbers. We had rational numbers, which are basically any number I can make a fraction out of 2 integers. So like -18, I can write as -18 over 1. -18 is an integer, 1 is an integer, and so on. And then we got introduced to these irrational numbers, things that cannot be written as fractions. In other words, they are real, which is kind of That's why they use a real number set. But um, they can't be expressed as a fraction. We don't know the exact value. In fact, there could be a whole math. There are a lot of attention by some mathematicians trying to figure out if they could find a pattern to um, pi or some of these other irrational numbers like square root of 2 could create a new science, because sciences usually have been discovered mathematically first. So it'd be interesting if they do find something. And with the onset of all this computing power, it might avail some kind of brute force kinds of methods to deal with some of these things. So that they really just can take on huge numbers or huge amounts of decimal places and those kinds of things to try to look for patterns. There's also a lot of efforts towards trying to find and be able to predict prime numbers, and that's an interesting field too. Well, in this diagram, so just a reminder, we should know this already about irrationals and rationals making up the real number set, and complexes are imaginary and reals, and then they kind of break down this complex imaginary and pure imaginary, which are just, this one is where a is equal to 0 in this addition, and this is where a is not equal to 0. So I'm not sure if there's any real value to realizing there's complex imaginary and pure imaginary. Not in this chapter will that be used, other than they might bring up those words anyhow. Well, okay, we got new numbers, so let's start just like we did in grade school. Is, they told us what the whole number set was, and then we started adding them together, and that's what they're going to do here. I'm going to do addition and subtraction, which should not be a real difficult thing when once you get past this idea what I is. And you just add or subtract, and you have to have like terms. Basically, you can't just take numbers out of this deal, because we have order of operations, and we have the commutative property and the associative property and the distributive property that are going to come up when we're dealing with this. So like example A, they're going to take this complex number 8 plus 6i and add it to this other complex number of 3 plus 2i. And here's the work they go through. Well, because it's all addition, I can change the order and I can group them differently. That's the commutative and associative properties. So they group the real portions of this complex number together and the imaginary numbers, parts of that. Okay? Probably why they bring up that pure imaginary, right? So here are the pure imaginaries, and here are just real numbers. Well, now I can add these as 11 plus, with the distributive property now here, I can say, well, I have a common factor of I, so I can factor that out and end up with 8i. Kind of looks like combining like terms, doesn't it? Okay? So we end up with this new complex number 11 plus 8i would be the sum. They say give me the sum of those two things. Remember, when you subtract, we need to add the opposite of the entire thing, and usually what I would do is change all the signs first. I would change this to be 4 plus 5i plus negative 6 plus 3i, and then I can change all the order of things if it's all addition, and which always kind of throws me in the book. They always do this. They say, well, instead of saying 4 plus a negative 6, they still say 4 minus 6. Well, we had to change to an addition to make that move, that change in order of the commutative property. I don't know why you'd have to go back to subtraction and so on. And especially here, this is where I see a lot of errors when you're subtracting a negative, right? So 5i, this is really 5i plus 3i, which is 8i, okay? But, you run into subtraction a lot. I always think it's a good, almost always the best method is to get rid of subtraction, get rid of divisions. And when I'm all in addition and all multiplication, I can use any order I want and I can group anything any way I want, which makes for a lot of simpler ways to do things. I can apply my commutative associative properties. So multiplication here, now when we have these square roots, it'd be very tempting to deal with this, but there's another thing that comes up with kind of like I. It's like it takes over order of operations. In other words, we need to deal with the I first before we start multiplying. Because it would be very easy to look at this and say the square root of a negative 2 times the square root of a negative 5 is the square root of 10, negative 2 times 5. And that is not true, okay? This is would miss the part. So the best way I know how to explain this is that, like I said, if you have an I, you have an imaginary number I involved, you have to deal with that first before you can do any other groupings in a sense. But if it's within a group, I guess the groupings take over. But then even before exponents, we have to deal with I in the complex number system. So they show the process here would be, well, this is the square root of a negative 1 times 2, square root of 2, which is I times square root of 2, and this is I times square root of 5, which ends up to be I squared times square root of 10. Now I squared is equal to something. It's equal to a negative 1. So we can perform that basically definition of I to be negative 1. So we end up with a negative square root of 10, or negative 1 times square root of 10. They give us that caution that I just talked about. This is not possible. You got to make sure that the trigger that occurs is we have complex numbers here that are occurring. We need to deal with my imaginary number issue first. With this in mind, it says, how can we now multiply? We can now multiply complex numbers. Because, well, we could go back to the definition and show that for us to have a square root of a negative, we end up with an addition occurring in there, which doesn't allow us to just go straight to multiplication. In reality, there's this a plus bi is occurring in here, and they want us to write it in that form. Okay. Well, the square root of a negative 4 times the square root of negative 5, well, that would be the square root of a negative 1 times the square root of 4, and times the square root of negative 1 times the square root of 25. In this case, we get I squared times 10. Well, I squared is equal to a negative 1. And so we get a negative 1 times 10. Okay? And so on. You can probably do these things too. And another way to deal with negatives too is you could go, I could change this to be I squared times 4 underneath this radical. So the radicand is I squared times 4, and this is I squared times 25. And so we end up with the square root of I to the 4th power times square root of 100, or 10. You could break it down a lot of different ways. Prime factoring. All the factoring rules work by, I could substitute, I could change the negative 1 that occurs in this factoring to I squared. And what is the square root of I squared? It's I, okay? And I just want to introduce that because there's going to be some times where that's going to simplify some stuff. And I really like applying this definition kind of order of operation issue is I can apply these definitions of I right at the beginning of this thing and not have to start doing math and remember that, hey, I got an issue with this first. I could change all these negative under radican in the radical to I squareds right away, and then I can do it in any order I want because now it's all multiplication. Again, that's kind of my philosophy towards, get rid of the subtractions, get rid of the divisions, get rid of the imaginary number issues by just substituting in the values for that issue to take care of those negatives, which would be I squared. Okay, so they go through several examples here, pretty much the same stuff. And then this last part here is using the distributive property. We have a complex number here multiplied times an imaginary number, or a less complex in a sense. It's so tempting to play with the words here a little bit, but so we'll do that here. They have this. You end up. Let's go to C first. Negative 3i times 8i ends up, now it's all multiplication here. It's 3 times I times 8 times I. Well, I can do that in any order I want. Negative 3 times 8 is 24. I times I is I squared. Well, I squared is really equal to negative 1, so I end up with a negative 24 times a negative 1, which is a positive 24. Here we have a pure imaginary number times a complex imaginary number, to pull out the words that they use, right? Well, you use the distributive property, negative 4i times 3, and I have to distribute that and go to negative 4 times a negative 5. Notice they changed to an addition. I really like that they did do that because, boy, there's a lot of sign issues going on here. Using a standard pattern of trying to get to addition first is, like I said, is probably less error prone. Well, negative 4i times 3 is a negative 12i, and negative 4i times a negative 5i is 20i squared. And then they changed the subtraction, but this is really negative 12i plus negative 20, because I squared you substitute with negative 1, and you end up with 20, negative 20, plus a negative 12i, I would sure take as an answer. And they go back to subtraction. And I can see, especially on my math labs, a lot of times it's sure a lot easier just to enter a subtraction symbol rather than plus a negative. So here they have two complex imaginary numbers. You have to use FOIL, right? First times first, outer times outer, inner times inner, last times last. In other words, distribute, use the distributive property. If you do it in this order, it brings your like terms together, so you can add more easily, at least part of them. These are like terms too in this case, okay? So you end up with that. Now, conjugates and division, we talked about multiplication, and we're going to run into a lot of issues that we're going to try to deal with in division. And it's kind of like radicals in the denominator and those kinds of things when we have an addition. And this conjugate is really based on the idea of what we get from difference of squares. And so if I have a plus b, right, let's say this whole thing is b. If I take that times a minus b, I get difference of squared, which is going to be this a squared times minus b squared. Well, we're going to end up with some real advantages from that. So they set up this idea of a conjugate, which is really its partner in the difference of squares types of multiplications. So we have a plus bi is, the complex number is a minus bi, and the conjugate of a minus bi is a plus bi. So they're saying it's if then or else situation, or infers both ways. Okay, they're going to give us this deal in And it really becomes kind of like y until you see some of the things we're going to need to do. So the first part of this lesson in this portion here is to get its conjugants, or what I like to say, its partner in the differences square type of multiplication, right? So if I have a negative 3 plus 7i, or minus 7i, its conjugate is negative 3 plus 7i. If I have 4i now, what is the first part of that complex number? It's 0 plus 4i. So its conjugate would be 0 minus 4i. It still would be like difference of square, except we don't have to deal with the 0. Complex numbers and their conjugants are real numbers, and that's what this really means. So how do I take two complex numbers, multiply two complex numbers together to get a real number? So if we want something in a fraction to be, say, well, I want the denominator to be a real number, we're going to use conjugants to take care of that. And here's where they basically bring up this difference of square thing. So if they multiply a number, this complex number times its conjugate, here's what happens. We end up with a real number, in this case 74. And they're using the difference of square shortcut that we've used. You know, you could use FOIL, but you'd find out that the middle term goes to 0. And we end up with the first term squared minus the second term squared. So I look at that and I say, well, it'd be 25 plus 49i squared, right? Or minus 49i squared, excuse me. Well, I squared is a real number. It is equal to negative 1. So we substitute that in for an I squared, and now we end up with just a real number. In fact, in this case, a rational number, right? Or a natural number, or a whole number. We could put different number sets to that, but it is real. It's in part of the real set, where these two were not. These were only in the complex number system. So conjugates can be used when dividing by imaginary numbers too. So if we divide and simplify to the form of this complex number a plus bi form, we have this division here. Let's look at example A as a negative 2 plus 9i divided by, in this case we're going to treat it as division, and we're going to say divided by this 1 minus this. Well, in a sense, we can also say, well, let's just change the denominator. Excuse me, I'm thinking ahead here when they talk about division. Is treated like a fraction, and we want to first go through a couple steps here, and let's look at this example. It says divide. To divide and simplify this division, we multiply by 1 using conjugate of the denominator to form 1. And I can do that, right? I can multiply any fraction by 1 and it never changes the value. But where we got this fraction, 1 plus 3i, is the conjugate, or its partner in this difference of squares kind of multiplication of this 1 minus 3i. Well, its conjugate is 1 plus 3i. Well, the only number I can multiply and not change the value of this fraction, this original fraction, it has to be 1. So I put it over itself, and that's 1. So they do the multiplication. Well, in this bottom denominator should go to a real number because I just multiplied by its conjugate. If that doesn't happen, or you don't see how that happens, then there's a problem. You know, you made a mistake with your conjugate, or you forgot about I squared being to a negative 1 or something, right? So I'm just going to step down. Look at our denominator. We end up with, here's the original times its conjugate. I end up with the first term squared minus the second term squared, which is 3i squared, which is 9i squared. Well, this is 1. 1 squared is 1. This is minus 9 times a negative 1, or negative 9. So I end up with 1 plus 9, which is 10. Okay. Now on top, let's look at the numerators now. Multiply the numerators. We need to do something. We have to do FOIL in this case because there's no difference in square kind of multiplying here. They get 2 times, they take first times first, they get 2, negative 2 times 1. Here's your first, the f of the FOIL is first times first, negative 2 times 1. Then outer times outer, negative 2 times 3i, which is a negative 6i. Inner times inner, 9i times 1 is 9i. Last times last, 9i times 3i, which is 27i squared. Well, here's an I squared, that's equal to negative 1, so they substitute for I squared as a negative 1, you end up with negative 2 plus 3i plus a negative 27, which simplifies to be negative 29 plus 3i all over 10. Now, they told us they wanted it into this complex number form. And here's another fraction deal. You got to remember saying, well, they want some real number plus a pure imaginary number. This is still a division. So we need to write it in that form. And I got to remember, how do I add fractions? Well, to do this, to have something over 10, each part of this addition has to be over 10, so they can do this. You know, it's easier kind of to see how it breaks out. We're used to dealing with things like this. Hey, they got the like denominator, I can just add numerators, right? Well, we can break out the numerator portions or the add-ins as long as we put them over the same denominator. Okay, and that's what they're trying to make you recall here. Now it's in the correct form. I have a real number plus a pure imaginary number. Now, conjugates of pure imaginaries, where the real part is 0, we don't necessarily have to deal with the 5 portion. We can just take care of the imaginary, because now it's just multiplication. I don't have distributive issues. I don't have to. The conjugate is really easy. I could say it's negative 5i, but if you remember what I squared means, I can get that I to be a real number just by getting to I squared. So I could multiply by I over I, and I end up with 5i times I, which is 5 squared, which is 5 times negative 1. So hey, my numerator, or my denominator, this fraction is real. I've taken care of that. And I've also created a lot less smaller numbers to deal with. This is really a good example to look at and not have to necessarily go to what are we really trying to do. We're trying to create a denominator that's real so I can write a addition in the proper form, really. Okay. So I take the I times the numerator, that does distribute, and I get 7i plus 4i squared all over negative 5, right? Well, here's an I squared, that's negative 1. So I get 7i plus negative 4 over negative 5 right here. They put them into subtraction. Well, how do I make that again into, break out that fractions? They have to have a common denominator. So I end up with negative 4 over negative 5 plus 7 over negative 5i. Or a better way to do this would be 4/5 plus a negative 7/5 I, or minus 7/5 I. So, like I said, we're going to talk about powers of I, and we're going to find that if you think about exponents, just like radicals, when you think about them as being fractional exponents, and if we can stay in this exponent world and remember our rules of exponents, you're going to save a lot of time and take less steps too. So they're pointing out this idea, well, if I have t squared, that's equal to negative 1. And then if I have I to the nth power, that's really I times I to the n minus 1. Now let me put some numbers to make sure this method here of using variables up here. If this was I to the 7th, I could say this is really I times I to the 7 minus 1, or I to the 6. Does I times I to the 6 equal I to the 7? Yes. So they're setting up that I have a pattern here, so that I can deal with. And it says if I have a negative 1 to the n power, and if the n is even, this always ends up to be 1, doesn't it? And if I have a negative 1 to the n power and the n is odd, I always end up with a negative 1. So they're kind of pointing out some stuff that we've already known, but they're going to use these patterns to help us create a simpler way to deal with I when it gets to higher powers.